Okay, hello guys. So I will be teaching the kinematics class for today. Do you guys have any questions from the previous set you want me to go through? Or do we just get right into it? You can direct message me any questions if you have. Okay, can you guys see my screen? Okay. So I'll just start first. If you guys have any questions, you can just message me directly along the way. Or if I'm going too fast, then you can slow me down. Wait, you guys can hear me, right? Okay. Uh, so just a quick overview for what we'll go through today. So I'll first introduce the kinematic equations, which are quite basic. I think most of you will be already familiar with it. And then we'll talk about the more advanced like SPhO related stuff, which is basically just applying the calculus you learned last week to physics problems. And then also we'll talk about some ideas which are like more higher order stuff. So like this stuff is more hard than more for like SPhO and above, but still very useful. Okay, so we'll get right into it. We'll start with the kinematic equations. So I'm sure these three equations, you guys are all familiar with it already. They are just the 1D kinematic equations. And then the more common thing you'll see in SPhO is probably like the projectile motion, which is you basically split it into two directions, and then you just apply the kinematic equation to each direction, like y and x. And then for the most common case of projectile motion is just you have a constant acceleration gravity downwards. So the horizontal velocity will remain unchanged. So if you just launch a projectile along the x and y axis, then it'll just go the shape will be a parabola. And then the vertical velocity at any point will experience some acceleration g downwards, whereas the horizontal velocity, which I will call Vx, Vx will remain unchanged. Okay, throughout the whole motion. So I think this stuff everyone is clear, right? If you need me to explain more in depth, can you message me please about this? Then if it's okay, I'll just move on. Okay, I'll just assume that you guys are all familiar with it already. So nowadays for SPhO is quite easy. So you can just do the same stuff as your H2. But we would like to introduce how SPhO problem might become harder in the math sense, which is by using calculus. So you need to be familiar at the SPhO level. You need to be very familiar with differentiation and integration. So like definitions of velocity like dr dt, you need to be comfortable with it, because sometimes the acceleration is no longer constant. So a is not constant anymore for some SPhO problems, and also in the problem set you'll see later lah. And then in the cases where the acceleration is not constant, these three default equations, they don't work anymore, right? So you will need to integrate in order to get your equations of motion. But usually the integrals won't be too hard, so don't need to worry about it. So for example 1, this is just simply, so it looks quite complex, but as I wrote on the screen here, basically it's just breaking up into the x, y, and z, which corresponds to I, j, and k. So if you guys are not familiar with this is like unit vector notation. So it basically just means x, y, and z corresponds to I, j, and k lah. And then the idea is you just break it up into each direction. So the I component go to I, the j component go to j, and you integrate them separately. So this, you integrate the first one, the I, you integrate the j. And then you can plug in the time, the limits for the time, which is 0 to 4. Okay, so actually it's the same idea, it's just breaking it up into each component. So this line is very important. Like basically you just bash it in each direction. Okay, and also now that we're working with vector notation, we need to take note that R is a vector. So bolded R, or this, you might see this type of notation, this just means it's a vector. So a vector has magnitude and also direction. So when you do dr dt, this you need to be careful that whether you're dealing with speed or velocity. So if you want to determine speed, you need to add the magnitude sign around, which basically just means you do this kind of adding, like the Pythagoras adding. The square brackets just mean magnitude here. So you need to be a bit careful about that. Yeah, anyway, this stuff is straightforward. And then acceleration is just a double derivative. So A is, we'll use vector notation here, is dv dt. And since v is dr dt, then you will have the second derivative of position with respect to time. Are you guys familiar with the R notation? So using R instead of x, y, z is usually quite common in 2D and 3D, but it basically just means, okay, so for example for 2D, when the y and the z look like that, we would represent a general direction as R, like this. Okay, so this is about polar coordinates, which we will introduce later. But anyways, TLDR is that R is just the position vector. So it's like, it can represent both your x and your y coordinate together. Yeah. Okay, moving on. So these equations are just using integration to prove the three equations that you already know for constant acceleration. So I will not spend much time on it. You can read through it. It's very straightforward. You do need to be careful for the integration limits. So it might not necessarily always go from 0 to time or 0 to v. So it could go from v0 to v or t0 to t. So you just need to be careful of the limits lah. And then there's this very common trick, we'll talk about this later, which is basically you can write a double derivative in terms of a single derivative, and the other one is a derivative with respect to position instead of time. So this is what we call a switching of variables. Oops. So it is useful if we don't want to explicitly integrate with respect to time and we want to integrate with respect to position instead. Okay, and you can see it being applied here to determine an equation, to determine the third kinematic equation, which does not have any time dependence in it. So this one does not have any time dependence. Yeah. Yeah, and as you might notice, right, the general form of the equations look quite similar to your 1D forms. So you don't need to be too intimidated by it. You can literally just write it in terms of each direction, x, y, and z. Don't need to do all this nonsense, but it's just to be complete. Okay, so example 1.2 is like a very, very typical kinematics question. You should be able to do it. It could appear in like H2 math, also, H2 physics also. So he falls freely from rest. So usually when questions say from rest, it just means the velocity is 0 at the start. It's basically telling you what your initial condition should be. And then it falls half the total distance during the last t. So you can just write your basic kinematic equations. S equals ut plus half at squared. So this is your s, your initial velocity times time, and this time it's g, the acceleration. And then you just solve the two simultaneous equations and you can get an answer for h, which is what the question is asking for. So yeah, this is a very straightforward example. Okay, now we'll talk about the more important stuff, or the more unfamiliar stuff, which is when the acceleration is not fixed. So this is very common, most commonly when there is air resistance. So if you guys did O-level physics or just regular SPhO, you will always deal with constant acceleration. But now that you guys are big boys and you have learned calculus, you can deal with air resistance also. So the most common form of air resistance is this one, which is linear air resistance. So it basically means that as your speed increases, your air resistance will also increase linearly. So instead of simply writing ma equals mg, which is when it's constant, now we have an extra term in our Newton's second law equation. So we will have this extra term m alpha v, which is due to the drag. Okay, and we also need to take care of this, be careful of the signs. So you need to define the signs properly. If you are wondering how we use negative, or whether you should use plus and plus, it's actually up to you, but you need to stay consistent. So if you choose, let's say like this, to be x and y, to be positive x, positive y, and your gravity is pointing down, then the sign in front of mg obviously has to be positive lah. But then if you flip your axis the other way around, so y is positive like this, which I don't really know why you do that, but you can, then you just need to be self-consistent. So make sure you know what you're doing yourself. But both is fine, as long as you're consistent. And then the negative sign in front of the drag term, this will always be negative. It's to signify that the drag always opposes the direction of motion. So if I'm going up, if my velocity is upwards, then my drag should be downwards, because that is the definition of drag. And then if I'm going down, if my particle is like falling down at some speed v, then obviously the drag will be upwards. This is air resistance. Okay, so moral of the story is just be careful that the air resistance one, you always need a negative sign in front. Then the gravity one, you can choose it however you want. Okay. Okay, so this is our Newton's second law equation with drag, and then you will need to, it's basically a differential equation in terms of v. So v as a function of time is our variable here, and this is a variable separable differential equation. So we can reorganize the terms. So we eliminate the m first, and then we bring over the g. So as you can see here, we bring over the g plus av to one side, so you have this form, and then we move all the t's to the other side, and then you integrate from some original speed to some final speed and some original time to final time. And then this can be solved with either a u substitution or a standard. If you remember the integral is okay. So if you guys remember how to solve this integral, you can let u equals g plus alpha v, and then du dv would be alpha, and then this will be your substitution. You can write dv equals to 1 over alpha du, and then your integral will become something along the lines of 1 over u du with some constant in front, and that's how the ln appears, because the integral of 1 over u is just ln. Okay, so this part is just math, applying what you've learned last week into a physical scenario. Okay, so to deal with problems with variable acceleration, you basically just need integration. That's the TLDR. And then the example also shows why signs are important. So the moral of the story is you need to be self-consistent. Make sure what you're writing makes physical sense. Is everything okay so far? If you guys have any questions, or if I'm going too fast, you can let me know. I will slow down. Okay, if everything is fine, then we'll move on. Oh, wait, sorry, I got a question. Oh, okay, so the question is how I go from the Newton's second law to the final equation. So in general, when we're dealing with problems with variable acceleration, so acceleration that is not constant, we need to first, step one is to write out the Newton's second law. So this part is your MA, okay, Newton's second law, and then this part is your net force, F net, so that is Newton's second law. And then after that, you can multiply throughout by dt, or you can simply think about it as you divide everything by this term. So what do I mean by that? Let me erase it. You divide both sides by negative mg minus m alpha v. So first we can cancel out the m's since they're all left on the same, since there's one on the left and also one on the right. And then you just move this one over. So it becomes 1 over g plus av dv dt is equals to 1. There's a negative sign here. And then now the next step is you multiply both sides by dt. And so you'll get 1 over g plus alpha v dv is equals to dt, and a negative sign here, okay, which is just this thing. And then this is just a variable separable integral. So you integrate with respect to v on the left, and you integrate with respect to t on the right. Then the integral of dt is just t. Integral of this thing, you need to do your u substitution. So let u equals g plus av. Okay. Okay, nice. Okay, moving on. So this is just what I said just now, and most famously, if you guys have watched Walter Lewin, which is this MIT professor, he does a lot of demonstrations. This is one of the demonstrations he does to prove that the kinematic equations work. He basically drops a monkey from some height, and then he aims the gun at where the monkey is originally. And then when you fire the gun and drop the monkey simultaneously, the gun will actually hit the monkey. The bullet will actually hit the monkey. So you can prove this for yourself by writing out the equations. So you can write the equation for the monkey, which is just a fall downwards. The displacement of the monkey is this one. This is just your S equals ut plus half at squared. But your u is 0, so this term is 0. But you have some initial starting height. And then you can also write out the displacement for y, and you see that it will be the same, which means that they have a similar vertical displacement in the time that it takes for the bullet to travel the distance d. So it will actually always hit the monkey. But there's also another way to prove that it will hit the monkey. I will go through that later. Yeah. So projectile motion questions always come down to algebra problems. You basically have to write a set of equations for the y direction. You have one equation, blah, blah, blah. And then for the x direction, you have another equation, blah, blah, blah. And then usually they'll ask you to find something. Maybe find the time, find the range, find the range, find the time, or some other thing. And then you just solve the simultaneous equation. Okay, so the next part is circular motion, which I think you guys will be kind of familiar already, but just as a recap, circular motion, especially uniform circular motion, is defined when the velocity is constant, and the radius is constant, but the direction of the velocity may not be constant. So actually, let me correct myself, the speed is constant, but the direction changes, therefore the velocity is not constant. So this is how we define the equivalent of distance. So in regular 1D motion, you write d equals dt. Then in circular motion, you will write s is equals to omega t, for example, where omega is the angular velocity. Okay, so you also have this, v equals r omega, and most notably, it means that objects which are rotating at the same angular frequency need not be at the same speed. For example, let's say this is your friend, and you are standing here with a yo-yo. So like you have a long string and the ball, and there's a ball on the end of the string. So if you shoot the yo-yo with a given amount of force, right? And then let's say that your angular velocity of the string is like omega. If your yo-yo was positioned here, so like if it was much shorter and it hits your friend, it won't be as pain, because the velocity, even though the angular velocity is the same, the raw velocity is not as big. Whereas if your length of the rope is super long and you swing it with a huge amount of angular velocity, then you're actually going to kill this person, because the distance is much larger, therefore the velocity is much higher. Okay? So the TLDR is that you can have the same angular velocity, but you do not need to have the same velocity because you have a factor of r. And then the definition for acceleration is r alpha, where alpha is just the derivative of the angular velocity with respect to time, just like how acceleration is dv dt. But also, most notably, you need to notice that there's a subscript here, which is that this is the theta means basically it's a perpendicular acceleration. So there are two types of possible acceleration. One is if you go in this direction. So if you go radially, so this is what we call radially. So it's along the radius. That's what we call radial. That's the radial direction. And then we also have tangential, which is like this. So when it's at 90 degrees, this is tangential. So these are the two most common, they're the two only types of acceleration. So for uniform circular motion, we are dealing with only radial acceleration. So if it's uniform, then the angular acceleration should be 0. But of course, you can also have some angular acceleration if it's non-uniform. And then there is this equation, very, very important, which is your centripetal acceleration. Basically, if you want to stay in a perfect circle, you need to have a constant radially inward force, denoted by Fc, which is the centripetal force. Then this is the formula. You guys need to know it, be familiar with it. There is a very popular question. I don't know whether you guys might have seen, so I'll just draw it over here. The question basically says if you have like the question basically says is that if you have a roller coaster and you want to, let me draw this better. So let's say you're at an amusement park and there's this roller coaster, and then the roller coaster is at some height above the ground, h, and then you also know that the radius of this is r. So h is bigger than r. So the question is, if I release my person, my cart down here, will it make it past the bend? So I will ask you guys, let's consider a few different cases. If h is smaller than r, will it make it past the top? So will it go over to the other side? What do you guys think? I think the answer should be quite obviously no, because if your height isn't as high, you don't have enough gravitational potential energy. So now I will rewrite the question. What if h is equals to r? Will it make it past the bend? Can you guys message me what you think? Yes or no answer. Okay, so someone says no. So I think you guys know the trick. So the answer is no indeed, because you cannot simply just do conservation of energy. You need to release it at some height higher than r. So the answer is no. Because when you reach the top of the circle, let's draw the forces acting on it. You actually have a gravity downwards. If your velocity is 0, it means that your centripetal force needed to stay in a circle is 0. But you have a non-zero force acting downwards. So that means you will not stay in circular motion, because you have a force when you shouldn't be having a force. So what will actually happen is you'll just fall down and die. So what we actually want to do is we want to match it perfectly such that at the top of the roller coaster, your Fc matches your Fg. So your gravity matches your centripetal force. So you might be asking, why do we only need to match it at the top? Why don't it like over here maybe or something? So the reason is because you can have a normal force also. Because if you imagine your roller coaster is here, you can have a normal force pointing inwards. So at any point that is not at the top, the velocity is actually higher than what it would be here because of conservation of energy. So the V over here, if I call it V1 versus V2, V1 will always be bigger than V2 by COE. And if V1 is bigger than V2, recall that our centripetal force is mv squared over r. And since our r is constant, a bigger V would mean a bigger centripetal force. So the centripetal force needed here will be always bigger than here. But we do not have to worry because that's the normal force. So we just need to take the limiting case, which is at the top, when the normal force goes to 0. that is the limiting case, and that will result in FC becoming FG. If you release it at speeds higher, so if H is even higher, it will not matter because the normal force will be able to produce the residual centripetal force needed to stay in a circle. You only need to match it just nice at the top where the normal force goes to 0. Okay, does everyone understand this part? If you guys don't understand what I'm saying or you're lost, please tell me. Okay, I will move on then. So, example 1.5. A particle moves in a circular path of radius r, blah blah blah. The angle it makes is a function of time, which means that it's not uniform circular motion. What are the values of tangential and radial components? So tangential and radial is just what I said just now, the one perpendicular to the radius and parallel to the radius. And then of the acceleration for t between 0 and t1. So you basically just apply, once again, when the acceleration is not constant, you would have to use the differential forms and some integration / differentiation. That's just how it is. And then you can get the answers by simply applying the definition of omega and alpha. Okay, so I will not dabble on this any longer. It is not the very hard part. Okay, so up to this point, are you guys all okay? If got question, please ask. Okay, I will assume that there's no questions. Okay, so now we'll go to the hard part. Some of these are quite relevant to SPhO, some of it is above SPhO level, but we'll go through it nonetheless. So one is polar coordinates. So just now I mentioned about this position vector, this R thing. Now I'll provide you with a formal introduction to a different set of coordinates. So what you've learned in school, which is like simply this. This is just what we call Cartesian coordinates. This is the most basic form, x, y, z, three-dimensional space. But in many rotation problems, it might be easier to work in a polar coordinate system, which basically just means instead of defining stuff as x and y, we defined it as r and theta for a 2D space. If you want a 3D space, you can use spherical or rectangular or cylindrical coordinates, but I'll not go through this here, it's not very relevant. But basically what these coordinates mean is you will have one coordinate r which points to the direction of your position. So let's say this is where your particle is currently. Then this line, this arrow r points towards the direction of your position from the origin. So this is the origin O. And then the second coordinate used to define is theta, okay, which is basically the angle your position vector makes with the x-axis. And then by some simple trigonometry, we can deduce the relationship between x, how to transform between the coordinates. We have x equals r cosine theta, y equals r sine theta. So notably, right, in Cartesian coordinates, our direction vectors are x hat and y hat, and maybe z hat also. But now we have r and theta, so we will have r hat and theta hat. Okay, so you can express any direction using these two, using a combination of these two. And as mentioned previously, theta is in this direction, is at 90 degrees to your r. And then you also have the other thing, which is your r hat, that one is just parallel to the r. So this is your r hat. Wait, sorry, it's the other direction. This is your r hat. Okay, so you can, any arbitrary direction of your velocity can be described by a combination of these two. So let's say if your velocity was pointing here, you can break it up into two perpendicular components, just like how you would in x and y coordinates. So you do one over here and one over here. Okay, so that is how the polar coordinates work. So if you want to be more formal, you can transform between the coordinates in this way. This is just, once again, trigonometry. And then to represent velocity and acceleration in the polar coordinate system, we need to consider both components. But the general case of any random motion, the r can change. It doesn't have to be circular motion. If r is constant, that is circular motion, but r can be changing. So we need to consider that case when there is acceleration in the r direction, and we will have these two equations. So if you want to see how these two, so right now it seems like they just appear out of nowhere, but I will scroll all the way down in the appendix. This is how it's actually derived. You can go read it through. It's not really that useful, so I will not go through it in class, but you can read it through if you want. The ending statement is that if you want to express the general acceleration in the polar coordinate system, you need to write it in terms of these two equations. So this one represents the acceleration radially. This is the acceleration tangentially. So if you want to see how it's derived, look below. There are a few things I would like to say about these two things. One is that if you notice, let's check the case for circular motion. For circular motion, our acceleration should be centripetal, right? So if we take the second term of our AR, we notice that this term looks oddly like our centripetal acceleration. Actually, sorry, I shouldn't write it like this. I should write AR is centripetal. AR is centripetal. So if AR is equals to centripetal, which is the second term, it means that R double dot must be 0. And this makes sense because what is R? R is the length of your position vector. Is this length, the length of this line, this black R line. In uniform circular motion, it doesn't change, right? It just remains constant. So your R double dot, the length of R double dot shouldn't change. Therefore, we see that the equation is consistent with the case of uniform circular motion. For the second equation, the tangential equations, the first term is actually what we call an Euler force or a fictitious force. So I will introduce more of this later, so don't need to worry about it now. The second one is something called a Coriolis force. So this is actually what causes wind and also hurricanes on Earth to move around. It's actually due to this force. Basically, when you're moving in a rotating frame, there will be an extra force acting on you. But don't worry about this for SPhO, it's not that important. What's more important is this. Okay? Okay, so here's an example applying the equations. You are given that the angular velocity is constant, but our position vector is changing with respect to time. So you basically do exactly what you do in x and y, it's just that now you're working in radial and tangential coordinates. You differentiate over here with respect to time, and then you plug it back into equation 25, which is your general case of acceleration. Once again, the left equation is more important. So you plug it into the equation for AR, and you will see that there are cases for AR to be equal to 0, which is the specific case when this condition is met. Okay? So there is a note here. It may be surprising that AR can be 0 even though the radial velocity is increasing with time. So this is due to changing directions of the basis vectors. So don't worry about it too much for now, it's not that important. But basically just note that there's nothing wrong with it. Okay? It's just because our coordinate system is now different. It's not fully the same as x and y transform into r. It's not as fully the same as x and y. Now we're working in r and theta. Okay, then the next is this thing. So actually this is very common in textbooks. You'll see it almost every time. And it actually even came up for SPhO last year as a whole problem, even though it's relatively simple. But the idea is that when you launch a projectile from a fixed position, so if you have a fixed position here, there is many different paths it could take depending on the angle you launch it at. And there is this boundary line, which is the red line, that encompasses all the possible paths the projectile can take. So in order to derive the equation of this path, we can use some simple mathematical facts with minimal physics. So if I draw this as my y, and this is my x. So as you can see in the comments, firstly is that you do not need to, actually, you don't even need to memorize you don't need to memorize this equation, but of course you need to memorize the envelope, the parabola equation, which is this. You should already know this by now. And then you just do some limiting cases. So the first is when the parabola needs to be symmetric about origin. So if you define the origin to be the launch position, then the b has to go to 0, because when you sub in x equals 0, you need it to be symmetric about this line. And then secondly is that it must be concave downwards. That one is self-explanatory. So alpha is a is smaller than 0. And then you can use the limiting cases, which is when theta is 90 degrees and when theta is 45 degrees. So when theta is 90 degrees, it just goes straight up. So when it's 90 degrees, it just goes straight up. And then you can use conservation of energy, which is v half mv naught squared equals to mgh. So h max is equals to v naught squared over 2g. And then when x is 0, y will have to be equal to this value, because we are defining the projectile launch position to be x equals 0. And then when the launching angle is theta equals 45 degrees, you will get the maximum range. So if you didn't already know this, you can prove this very simply using some differentiation. So if you launch a projectile at an angle at theta, we know that the range formula is v squared sine 2 theta over g. And then you can just differentiate the range with respect to theta, and you should see that theta will come out to 45 degrees and set it to 0. Okay? And this also makes intuitive sense, because if you launch it higher, you won't have as much horizontal speed. If you launch it lower, then you won't be in the air for as long. So 45 degrees strikes a balance between the two. Okay, so that is when the range is maximum. Then you just plug in the conditions that at this point y equals 0, and then the x is the maximum range formula. Okay? So you can basically solve for A and C. You can solve for C by using condition number 3, and solve for A by using condition number 4. And that will allow you to get the final form of the equation, which is this. Okay? So, show you the power of considering extreme cases and logical deduction. This is quite self-explanatory. You can look at limiting cases to see whether your answer makes sense. Okay, so we'll do example 1.7, which is applying what we've learned here. A projectile is shot from the origin with the smallest possible launching speed. that allows it to hit the target on the ground some distance away. Show that launching velocity is perpendicular to the final velocity. So first of all, you need to be, I think you guys already know, right? This is in the math syllabus. If you have a perpendicular line with gradient m1, a set of perpendicular lines with gradient m1 and m2, then m1 times m2 should be equals to -1. This is just properties of the line. Okay? And note that gradient is dy dx. So if the projectile has a path of y as a function of x, then the gradient m will be just dy dx. Okay? And therefore that's where this condition comes from. Dy dx is also the slope of the tangent, and we also know that velocity is parallel to the slope of the path, which makes sense. Like if your parabola is like that, your velocity will be perpendicular at every point to whatever the slope is. This equation is a bit out of the blue, but it's actually very easily derivable. You basically just set your, this is a very standard equation. You don't need to memorize it, but you can just derive it. If you have launching angle V0 and theta, then your Vx is V0 cosine theta, Vy is V0 sine theta. And then you have an equation for x of time. So x of time will be equals to V0 cosine theta times t. And then y as a function of time will be Vy, which is this thing, I have no space, minus half gt squared. And you basically write t as a function of x here, and then you plug it into this equation to get y as a function of x. Okay, so I will not walk through the math, you can do it yourself, but that's basically how you get equation 27. And then we differentiate this equation because this is the actual trajectory, and we get this. So note here that x prime is the position of the target, as how we defined it previously. Since the question states that it barely hits the target, like smallest possible launching speed, then we need to consider the extreme case, which is exactly what the projectile envelope allows us to calculate. So the cyan curve is for when theta equals to 45. And we can then combine equation 26 and 27 to isolate and solve for the angle theta. Isolate and prove that the launching velocity and the final velocity need to be perpendicular. So you basically just do this one, you set this equation to be equals to this equation for x equals x prime. You'll get this quadratic. Quadratic, and then you will solve for the quadratic for tangent theta. We also know that the gradient at any point is tangent theta equals dy dx. So that's how this comes about. And therefore, you can prove that the initial velocity and final velocity are perpendicular, because one is this one, this is this one, and then if you do negative gx prime over v0 square times v0 square over gx prime, you'll get -1. Okay, so this question uses a bit of math mainly, and also our projectile envelope. Any questions? Okay, moving on. So the next one is very, very useful actually, and I personally think it's very, very neat. Okay, so I don't know what this diagram is though. Like, I don't know what Pro is doing when they put it in. I will just talk about what I think is useful, which is that, so I have an empty page here. So frames of reference are useful because sometimes, right, there's a lot of things moving, and it's confusing to study every single thing and write Newton's second law. So I'll illustrate this with a very, very common example. You'll see this everywhere, or you'll encounter it sooner or later. So you have a wedge, and you have a block on the wedge. So I'll call this M1, I'll call this small m and this big M. Okay? And then this angle is like theta. So this will slide down, obviously, with acceleration g sine theta. But more importantly, in this case, we do not fix the wedge. So as the block like comes down, the big M will actually go to the right. So I'll write it as A small m and A big M. Okay, so the motion is not very simple. The acceleration of m is no longer just g sine theta because the wedge can move. So what do we do now? Well, if we go into the frame of big M, so I'll draw a box to denote that this is the frame of M. If we go into this frame, right, what we notice is that the motion is very clear. It is just sliding down the slope. So we would want to work in the frame of big M because in the frame of big M, we know what's going to happen. It's very easy to predict what will happen in the frame of big M. But it's not so easy to predict what will happen in the lab frame, which is in the original frame I'm working in. So, but there are some caveats that we have to take note of when we move into a moving frame. So first is that there are two types of moving frames, I should say. Inertial versus non-inertial. So you might have heard this word before. It's basically just a very fancy way of saying this is stationary or constant. Okay, so inertial is basically just a stationary frame or a frame moving at constant velocity. And a non-inertial frame is just an accelerating frame. So it's fancy words. And then for the first case, right, this frame is easy. If you go into a moving frame with constant velocity, then you simply give the object in your moving frame the velocity to the right, to the opposite direction, I mean. Very atypical example is if you're in a car and you're just sitting in a car moving forward speed v. If you look at what you see, right, it appears to you that the world is moving to the left with speed v in your frame. So this is basically just a Galilean transform. It's a very, very like intuitive idea. So I think this one is clear. But when you go into an accelerating frame, which is what we see here, stuff is not as simple. You cannot simply give it an acceleration. Actually, you can. That's what we call fictitious force. But you cannot simply give it the velocity in the other direction anymore. So you need to introduce something called fictitious force, which is what is mentioned below here in a non-inertial frame. Okay? What is a fictitious force and how do I use it? Well, if you go into an accelerating frame, it can be any kind of frame, but for the purposes of the example, we'll consider a translationally accelerating frame. So the acceleration is just along a straight line. Okay, so the frame is moving at some acceleration a. then all the objects in this frame, be it a wedge, a ball, or a block, will experience a force in the opposite direction equal to the mass times the acceleration of the frame. So let's be clear. The force is opposite the direction that the frame is accelerating in. Okay? And is equals to the mass of the object times the acceleration of the frame. So in the example of this block sliding down a wedge, the force experienced by this block will not only be mg sine theta, so there will be one along the slope, mg sine theta, but there will also be an extra force acting horizontally. Let me erase this. So this is the usual gravity, but then there will also be an extra fictitious force here, which I'll call F. Okay, and then you also have normal force now. Okay, so the sum of these three forces should give you sliding down a ramp nicely. i.e., if we consider the forces along the wedge, we should have Fg, which is mg sine theta, minus Ff. So we need to do a bit of angle chasing here. So if this is this will be theta. So this is 90 minus theta. Yeah, so this will be theta. So you need to do Ff cosine of theta is equals to ma. This acceleration is just the acceleration of the block down the slope in the moving frame. Okay, so in this specific question, it's a problem from a Russian. It's from a Russian book. It's basically asking for the time it takes for it to reach the bottom of the ramp. So time is invariant under changing of frames. So if you know the acceleration in this frame, you can calculate how long it will take to slide down the ramp by simply doing s equals half at squared, where s is the length of the ramp. And then you might be asking, how do we get small a, right? Because that's another unknown. You simply do conservation of momentum. So big M times AM has to equals to M times small am times cosine theta or sine theta or something lah. Okay, so you have this equation, and then you will have to use another condition, which is that AM is geometrically related to your the A small m is geometrically related to your A big M. You need to draw like a triangle to depict this. So like, let's say this is my AM, A big M, and then this is my G small m. So the vector sum of this will be my A small m, if that makes sense. So you need to use this geometric constraint to be able to solve for your small a exactly. Okay, but this I won't go through this problem in depth and solve it because it will be gone through in dynamics. I'm just using it to show the idea or the power of a moving frame. Okay, and also the example 1.8 shows you how you can use a moving frame to immediately tell the answer to a problem. You can read example 8 yourself, 1.8 yourself. But what I actually want to say is that for the monkey problem just now, if you go into the moving frame, you can actually see that the dart will always hit the monkey. Because when it's accelerating downwards, right, if you go into a frame that's accelerating downwards with g, then let's say this is the bullet will experience in this frame, in this accelerating frame, the bullet will experience some acceleration upwards, which is exactly g. And then your monkey, which is falling down, okay, I drew it as a human, but you get the point. It also has a force going up. So they both have the same acceleration going up, and this one was aimed along the line that is like that is joining the two. It's going in this direction. So if they both have the same acceleration going up, it'll definitely hit lah, because the vertical displacement will definitely be the same, and then it'll just be along a straight line collision path, if that makes sense. Okay, so that's how you tell that it is immediately obvious it will hit the monkey. Example 1.8, you can read through it yourself. And then the last thing that I want to talk about is optimization. So after this, you can have a short break, I guess. Okay, so optimization is very, very common. Very, very common in SPhO, as you will see in the problems later. And actually, to illustrate optimization and this specific idea, I would like to use an example. So traditionally, right, you have learned the brute force way of optimizing, which is you write the parameter. Let's say you want to optimize y as a function of x. So you want the biggest or smallest value of x, the biggest or smallest value of y, and what the x corresponds to. So you would simply just take a derivative and set the derivative to be 0, because that is a stationary point along the curve. So it's a maximum, a local maximum or a minimum. However, this method is not always the fastest. While it always works, sometimes the equations can get very, very messy and it's impossible to differentiate. So we would like to suggest an alternative, which uses Fermat's principle. Basically, what this says is that light always takes the shortest path. So light is a slacker. It will find the shortest path and it will always go that way. So if you have seen refraction of light, when it would have this weird bending thing to go like this. So this happens because the refractive index is different, which means that a straight line path is no longer the shortest. This kind of bendy path is actually the shortest to get from point A to point B. So to get from point A, which is for example here, to point B, it wouldn't take this straight line path because it's not optimal. The light will travel slower in here than here. So instead it will do this bendy thing, which is basically your refraction. Okay, so that is what I mean by light always takes the shortest path. It will not go in a straight line if the refractive index is different, because when the refractive index is different, the speed of light is different. So we can use this idea to write this equation, okay, which relates the ratio of the speeds to the entry angles that optimizes a path from A to B. So if the speed in here is v1 and the speed in here is v2, then the optimal path to get from A to B is no longer a straight line. It will be this refractive path, and we can relate it by using Snell's law, which is rewritten into this form. Okay, so now you might be wondering, how would this ever be useful? So let's have a look at an example. So this problem is very nice in the sense that you can use both methods to solve it. A man who is capable of running 4 meters per second and swimming 2 meters per second wishes to cross a river, blah blah blah. I'll first go through the differentiation way, So the way you would do this problem is first define the length b at which he will enter the river. So he wouldn't go a straight line because running on land is faster. So he will probably run a bit and then swim across. See how it goes. So we write the point at which he enters. We name that b, and b is the distance x from a, and then we can write t as a function of x. And this is actually equals to x over v run plus square root L minus x square plus d square over v swim. So the reason is because we just use Pythagoras theorem lah. There's a square root goes over here. And then also we can write this further as x over 4 plus, okay, I won't go through the math fully, but you get the idea. We write t as a function of x. And to minimize this formula, we can do dt dx. Set this to 0. And we should get x is equals to 142.26 meters if you work through the math. And then you can simply calculate the time, which is just x over v run. So the total time is x over v run plus whatever this length is, which is some L minus x plus d square over v square, blah, blah, blah. Okay, and you just plug it in lah, basically. You plug this value of x in, you will get the correct answer. But this is the lame method. The sigmas use method 2, which is Snell's law. So the way you apply this is you use the equation we derived just now. If you want to get from A to B, and the ratio is V1, V2, this is alpha 1, alpha 2, then you would want to use your equation sine alpha 1 is equals to V1 over sine alpha 1 over sine alpha 2 is equals to V1 over V2. So we have sine alpha 1, so oops, sine alpha okay. So if we apply it to this context, so if we call this running and we call this swimming, we see that sine, wait, what the? So we see that if we call this our alpha 2 and this is our alpha 1, we see that alpha 1 is actually equals to 90 degrees. So applying our formula just now, which is sine alpha 1 over sine alpha 2, so you have sine, wait, my bad. You have sine alpha 1, sine 90 degrees over sine alpha 2 is equals to V run over V swim. Okay, and you can then determine what the angle is. Alpha 2 should be equals to sine inverse. So this is just equals to 1. V run over V swim, V swim over V run. So it's sine inverse of 0.5, which is equals to 30 degrees. So we immediately determine the angle it has to be launched at, or should I say it should, the angle between the normal and the path BC for it to be optimized. And that will immediately give you the answer already, because then you will be able to calculate x. L minus x, L being 200. Wait, sorry, 100 tangent beta should be equals to L minus X. Okay? And then you know what beta is, you know what L is, you can get X immediately. So this is faster than differentiating, much faster. Okay? So is everyone clear with this alternative method? So this is an example question. It's not in the notes. You can copy it down. So it's an example to illustrate the power of this. Any questions? Okay, if there's no questions, then, oh, there's one last thing, which is the change of variables trick. Okay, so just now earlier in the problem set, right, you saw this acceleration, which was d squared r dt squared being written as r dot dr, and this looked very, very strange. So the way we do it is we use properties of derivatives and also what we can do with differentials mentioned in the previous set. So we can write the second derivative of x with respect to time as dx dot dt, and then dx dot dt can be written as this thing times this thing, because remember, differentials can be treated like fractions, so we can actually cancel out dx to see that they're equal. It's like a scan method. And then dx dot dx is just this thing, dx dt is x dot. So that is how this trick arises. You can also write it as this, but personally I've always used this one, the first one. I think the second one is useful also, but I've always just used the first. And this is a very, very useful trick. You'll use it not just in kinematics, but everywhere. Dynamics, electromagnetism, anything you can think about. And a general idea is that this doesn't apply just to position, it applies to any derivative. So if you have any arbitrary derivative r double dot, you can write it as r dot dr. Okay, so if it's x, you can also do it. If it's y, you can do it. It can be anything. This is a general trick that you need to know. It's useful because sometimes integrating an expression with respect to time is not the best. Opting to integrate with respect to position is better. And this will be illustrated in problem 2.14. Okay, so you can work through it if you want. It's a slightly tedious problem, but not too physically difficult. Okay, so that's it for the content wise. Do you guys have any questions? So I think the harder parts are mainly this Snell's law thing. It might be quite unfamiliar and also quite groundbreaking. I think the fictitious force one is also a bit tricky, but don't worry, next lesson we'll go more in depth. Everything else should be quite standard, right? Okay, if there's no question, then we'll take a 5-minute break and then I'll go through some of the harder questions. I have a few requests. If you guys have any requests, can also message me during the break or any questions. Okay, so be back by 9:20, please. Okay, are you guys back? No. Okay. Okay, I got a request to do problem 2.15. Wow, okay, not bad. So, before that, I think all the questions from 1 to 12 are quite doable. 2.13, to do it with the intended solution is quite difficult. It requires quite an ingenious thought. But you can give it a try. 2.14 is actually doable. It's only the math is hard. And then 2.15 and 2.16 are quite tricky. Okay, so for 2.15, the setup is that there's a spider pulling a cord and there's a snail that's crawling on the cord. And we want to find the time it takes for the snail to reach the end of the what's that called? The web. Wait, I forgot what I was gonna say. The web of the spider. Okay, whatever. I forgot what the word was. But, anyways, okay, hang on. I'll go through 2.15 first. So the first step to solving this problem is we first can write a very, very general, like we write some general statements, which is that this end of the cord, it moves at a fixed speed. So we can write the length of the cord, if this is L, this is a function of time, and it's equals to L naught plus U times the time elapsed, because they said the initial length is L naught, so it's not 0. Okay? And then this is the tricky part. What is the speed of the snail? So it's given that the snail's speed is v in the moving frame, but this speed is relative to the cord. And actually, right, what you need to know is that this cord does not have a fixed, like each point of the cord is not the same speed u. Because if you think about it, right, let's say this is the whole cord, this is the whole length of the cord, L. I can break it up into many, many small sub pieces. If this is the wall, at the edge of the wall, the speed must be 0 because you're connected to the wall. You cannot move anywhere. Whereas at this end, it must be u because you need to match the spider's speed. So actually, right, the speed of each little portion of string is linear according to the length. So as you go more and more out, the speed actually increases according to the distance. So if I write the point as v cord, it's actually linear in terms of length, x over L times u. So when x is 0, v is 0. When x is L, v is u. Okay, so if you're wondering how I get this x over L, this is a proportionality factor because each of these length elements, you can treat them as fixed. But as you go longer and longer, right, they kind of compound. So like the velocity over here is equals to this velocity plus this velocity plus this velocity. Because each chord piece itself is moving. And then this is moving with respect to the previous chord piece. So as you get longer and longer, it actually increases linearly from 0 to L. If that makes sense. The piece before it gets longer, this piece also gets longer, this piece will get longer, this piece will get longer. So overall, this one will get longer by even more. Does that make sense? Why isn't it x over L naught plus ut? Okay, because you need to consider the limiting case. So we know that the velocity is linear in terms of length, so we can let's just write it as m in general first. m times u. If you plug in what you said, which is that it should be 1 over L naught plus ut. Oh, sorry, x over L naught plus ut. Then at time, oh wait, no, it is what? Because L is equals L naught plus ut what? You're correct what? Right? Like this L is just the general expression for the length as a function of time. It's not L naught. Yeah. Okay. So then we use the fact that the speeds were add. Oh, can you explain how the okay? So I'm explaining this part again. So let me re-explain what I said. So we know that the end of the of the chord moves at a certain speed. Okay, so I'll call the distance L because and the function is given by L naught plus ut. So at any point in time, let's say the snail is over here, a distance x. Okay, the speed, which I'm going to call v, is equals to u plus the speed, like how to say, relative to the u is the speed relative to the chord, but it also has some speed itself because the chord itself is moving, right? Like the lap frame speed is v chord plus u. So we want to find what the chord speed is, and the way you do that is by using the fact that it's linearly proportional. So if you imagine breaking up this very long chord into many small pieces, each of them get longer. So over time, right, it'll become like this, and like this. So this one actually moves more than the rest. The displacement of this one is very big, and it's actually linear with respect to the original position. And then we use the fact that at the wall, which is when x equals 0, the velocity of the chord should be 0 because it has to be attached to the wall. And then at x equals L, the velocity of the chord has to be u. I think the tricky part is to observe this one. Do you understand this part? Like why the speed will increase? It's because each piece is getting longer. Each piece before that is getting longer. So overall, as you go further and further out, they actually get longer as a whole, if that makes sense. Okay? Does that make sense? Okay, then the next part is once you have a function for the v chord, then we can write a differential equation. So first we use this one. So the v in the lap frame, so note that the v here is lap. This is, I should clarify, this is the lap frame. Is equals to the chord, which is x over L of t, which is equals to L naught plus ut times u plus v plus u, sorry. Where's my eraser not working? Oh wait, they already used v. Okay, wait, sorry. I need to rename everything. So this is, I'll name this v lap, and then the u should be v. And so v lap should be equals to u over L naught plus ut times x plus v. Okay? So this is the speed in the lap frame, which is equals to the speed of the chord times the speed relative to the chord. Plus the speed relative to the chord. Up to this point is okay? So now we observe that v lap is just dx dt by definition. So we get this differential equation okay, so there are two ways to solve this. You can use integrating factor. This is a differential equation, or you can use, let me think, can you use variable separable? No, I don't think you can use. Yeah, okay, I think you need to use integrating factor. This is not variable separable. So you can use the fact that the integrating factor I of x is e to the integral negative u over L naught ut dt, right? Yeah, okay. And this is equals to, so the top integral, you can do a u substitution to solve it. I think it's this. And then this and this cancel. So you're just left with 1 over L naught plus ut. So this is your integrating factor, and you need to remember, you need to multiply the integrating factor to both sides. So you will then in turn get this equation. So multiply I of x to both sides, d dt x L naught plus ut I think. Yeah. Okay, and then you just solve lah. I'm a bit lazy to do through the math. But you should, the final form, you should be able to get x as a function of t, I believe. Yeah, you should get x, so like a function for x in terms of t. And then when the snail reaches the other end, that is when x is equals to L naught plus ut final. So you basically plug in the condition that L naught plus ut final is equals to x of t final, as in like your equation for x lah, your function for x. So let me look at the answer key. The x of t should be equals to, oh my god, it's a bit long, L naught plus ut times v over u ln L naught plus ut over L naught. So then you just plug in t final. So you, instead of writing t, you just write t final to both sides. So you move this over. Okay, and then you have an expression for t final in terms of all this nonsense. Which shouldn't be too hard because this and this will cancel. So you're left with u over v is equals to ln blah blah blah. Okay, and then your t should be equals to blah blah blah, some constant. So this part after that is just math. The physics is mainly setting up this differential equation right here. This is the physics part. Okay, so the key learning point is this kind of linear extending thing. It is not the only time this idea is going to appear. So the way we pick problems is we pick those that have potential to come out again. And actually in oscillations, right, there is this thing, so you always deal with massless springs. So we neglect the mass of the springs. But actually, right, in real life springs have mass. So like for a length of spring dx, it actually has some density. And in this case, right, you actually need to use integration to determine what the oscillation frequency is. The oscillation frequency is no longer just square root k over m for a spring with mass. Oh my god, my handwriting is atrocious. Okay, but the idea is that you will need to invoke this linear extension thing again. Okay, so this is the key learning point here, the physics. This part is just math, solving the differential equation. This is the key learning point, which is that the extensions of each chord component will compound linearly. Then you will need to be able to set up this equation. Is it okay? Ken? Any questions? Okay, if there's no questions, then let me see. Do you guys have any other question requests? Oh wait, there's one more, right? 2.13. 2.13. What is 2.13? Oh, this one. Lamau. I actually found this problem from a YouTube video. It is very nice. Why can't I extrapolate? Wait, what do you mean extrapolate such that the bottom is 45? Like you want here to be 45 degrees, is it? The left part of the graph. Like the launch angle? So like you want this to be 45? Oh. Okay, I understand what you mean. You're saying you want this over here, right? And then this be 45. Yeah. No, but that doesn't maximize, like the range here is not this one, right? Like you're trying to maximize this range. Like if you do that extrapolation thing, you're maximizing the full range. Okay, I'll give you an example, okay? Let's say if it was like this, like slightly a bit worse than 45. Perhaps your full range might be shorter, but more part of the graph will go to here instead of here. Like if you know what I mean. Yeah. Because like this only maximizes the full one, but you're not maximizing the full one, you're maximizing this part instead. Do you want me to go through like how to solve this thing? Or do you want to try it yourself? Only the geometric part. Okay. Anyways, there's a YouTube video that is in the solution. So the idea is that if we let the original launch angle be, let's call the original speed be v naught. Okay, did I give it? Ah shit, I think I forgot to give it. It's given, the original speed is v naught. And then yeah, v naught is given. My apologies. And then we note that the distance it travels is equals to t times vh, vx lah, I'll call it vx. So this is x and this is y. So the range is like t times vx, where vx is the horizontal velocity. Okay, and then we also know that the final velocity, which I'm going to denote by vf, is equals to square root. Do you guys know how this comes about? It's just conservation of energy. So half mvf squared on the left and half mv naught squared plus 2gh on the right. 2mgh. This is just, I'll write here COE. Okay, but the cool part is, the cool geometric part is this thing. So if we draw the original line, right? So let this be the original line of V naught, and let this be the final length of VF. So this is arbitrary length. Then we have the change in the vectors. This change is equals to G times T. Do you guys agree? Because the only force to act on it is gravity. So there is G downwards. So actually the change in the magnitude of the vector, the change in the vector is GT. And this is perfectly vertical. So if we consider, so this triangle can take many different shapes, right? It could look like this, it could look like this. Oops. It could look like this. Or something, I don't know. It could take many different forms. The key insight here is that if you look at the equation for range, T times Vx, and you look at the area, okay? Key is to look at the area of triangle. The area of the triangle is equals to half times base times height, right? And if we let our base be the GT side, it will be half times GT times VH. Or should I say VX? Sorry, not VH. So this horizontal part is Vx, right? Agree? This is the formula for a triangle. Okay, now we observe the similarities. Our range is T times Vx. So can you see that these two terms, T times Vx and T times Vx, are actually the same? So the area and the range differs only by the constant in front, which is half times G. It differs only by that factor. Which means, if we want to maximize R, we need to maximize the area of the triangle. Okay, so here is the cool part. And we also observe that VF is fixed, or the magnitude of VF is fixed. It has to be V0 squared plus 2GH, all of which are constants. So I shall now redraw this triangle. So if this is VF, the other way we can express the area of this triangle is by using half times base times height, but with a different base and a different height. So if this is V0, this height will be half times VF times this length. Okay, so I'll highlight this length. It will be this length. Half times the yellow thing. Now, we observe that VF is fixed. So we can adjust V0 to be like this, like this, like this, like this, however we want. But V0 will always be less than if it was a straight line, because the magnitude of V0 is fixed. So it will always be less than this if it was just a perfect straight line. So the maximum area therefore occurs when this is at 90 degrees. Because if it was here, it would be smaller area. If that makes sense. As in, this component will always be V0 like cosine something or sine something, which is less than 1. So the yellow part will always be less than V0 unless it's at 90 degrees. Then it will be exactly V0. And this is what maximizes the area. Okay? So from here on out, it's just very simple math, just a bit of trigo. So if we know that this is at 90 degrees and this is angle theta, then we can angle chase this angle should also be theta, and then we can write the optimum angle is tangent theta max equals V0 over V final. And we also know that V final is equals to V0 squared plus 2GH. And this is the final answer. Quite neat, right? Do you guys have any questions about the logic? Okay, so the key insight here is that sometimes to maximize something, we don't need to maximize it head on. We don't need to brute force it. We can find something similar to it that is easier to maximize. So this is the idea behind geometric methods, which is that you can express something in terms of something else, or two things are related by a certain factor. And in order to maximize one thing, you can maximize another instead. The other common example will be if you have something like A, which can change, plus a constant C equals B. The question asks you to optimize B. You can actually optimize A instead. And sometimes the other thing might be easier to optimize. So you will encounter these examples in the future again, which is why we think it's worth learning. Okay, but anyways, there's a typo, which is that there should be at velocity v naught. Okay. Do you guys have any other questions? Okay, if there's no other questions, then you guys can go and attempt the rest of the problem set. Like I said, I think it's all quite doable. Even up to 2.16, it's all quite doable. I think some of you have already done up there, which is very good. And then the advanced problems are just there for fun lah. They will never be tested in SPhO. It's way too difficult. But if you find the previous ones easy, you can go and do them. Yeah, okay, that's about it from me. Do you guys have any other questions? You can ask stuff not related to the problem set also. Like, I think are any of you from RI here? I think one of you are, right? Like, for RI, there is an internal selection test, I've been told, which is in late August. We compiled last year's selection test paper. So if you need it, you can message me, or we will maybe send it in this chat. Yeah. Okay, that's it from me. If there's no questions, then you guys can leave. Bye bye.